Welcome to IIOCS.com Food Tech Club. Today we will be learning about water activity and its relation to food spoilage. We all know that moisture content is the quantity of water contained in a material. It is important to consider the moisture content of the food material to know if the food is suitable for the consumption. How? Because moisture content affects the physical, chemical and microbiological aspects of food. The moisture content of the food relates with the freshness and stability for the storage of products and various other aspects in the food processing industry. A knowledge of the moisture content alone is not sufficient to predict the stability of foods. For example, jams contain about 30% of water, but that water is bound to sugar and is not free to support the growth of bacteria. Yes, students, we have many preserved foods like jams, pickles and all. So the moisture content in the jam microorganisms cannot grow in that. Why? Because it is preserved. So then what is that factor which is affecting the food processes in the products? Okay, so let's see that in the next slide. Some other examples are, some foods are unstable at a low moisture content. For example, in peanuts, the peanut oil deteriorates if the moisture content exceeds 0.6%, whereas other foods are stable at relatively high moisture contents. For example, potato starch is stable at 20% moisture. So let us see the reason behind all these things. So it is the availability of water for microbial, enzymatic or chemical activity that determines the shelf life of a food. Okay, it is the availability of water. How much water is available for any of the microbial growth or any chemical activities. So the degree of availability of water is measured by water activity. Therefore, water activity is nothing but water availability. So the available water for any reactions is the water activity. Based on this availability of water, so we have classified the water as free and bound water. We have studied this in the previous chapter, right? So free and bound water. Free water is the one which is available for any microbial growth or chemical reactions, and bound water is the one which is bound to other components of the food and they are not available for any chemical reactions or microbial growth. Therefore, the term water activity describes the amount of water available for hydration of materials. So this water activity is nothing but the activity of free water, right? It's about the activity of free water. Yeah. Let us see the definition of water activity. Water activity is defined as the ratio of the vapor pressure of water in a material to the vapor pressure of pure water at the same temperature. So the water activity is nothing but vapor pressure of a particular food material when it is compared to the vapor pressure of pure water. So let us see what is vapor pressure. Vapor pressure is the pressure formed by the vapor escaped from the food over the surface of the food. So vapor pressure is the pressure exerted by the vapor, okay, which has escaped from the food. So they exert some pressure on the surface of the food. So that is nothing but vapor pressure. So in water activity, so we can compare the vapor pressure of the food with the vapor pressure of pure water. Okay. The size of the vapor pressure depends on, the size in the sense the quantity of the vapor pressure depends on the amount of water present in the food. Then temperature, the temperature required to mobilize the water or the vapor from the food. Then the concentration of dissolved solutes. Okay, so the dissolved solutes matter a lot, right? So dissolved solutes may convert the free water to bound water, so that we don't want, right? So water activity is basically about free water. So the factors which affect vapor pressure are the water present in the amount of water present in the food, then the temperature required to mobilize that vapor from the food, and then the concentration of dissolved solutes like salts and sugars in the water. Let us see how water activity is measured. Water activity is measured in values from 0 to 1. Okay, 0 is for the food product which is completely dry. Okay, need not be a food product. So any material which is completely dry without having even a little bit of water, the value of water activity will be 0. And for pure distilled water, it is 1. Okay, that means the range of water activity is between 0 to 1. When liquid water is all available for hydration of materials, then water activity is 1. So when liquid water, that is pure water, when it is completely available for hydration, right? So it is completely free to react. So the water activity is 1. And when none is available, when no water, free water is available, the water activity is 0. Multiplication of water activity by 100 gives the equilibrium relative humidity in percentage. So that is nothing but, so we know that water activity is the vapor pressure of food is to the vapor pressure of pure water. Okay, when we multiply this value with 100, it gives the percentage. Okay, the percentage of equilibrium relative humidity. So let us see one example here. So if we take the water activity of some food product as 0.80, then it means the vapor pressure is 80% of that of pure water. When compared to pure water, so the vapor pressure is 80%. Okay. So let us see the definition of equilibrium relative humidity. Equilibrium relative humidity is the relative humidity of the atmosphere at a particular temperature at which a material neither gains nor loses moisture. So relative humidity is, in simple words, it is the moisture content present in the air which surrounds the food. Okay, relative humidity is the moisture content in the air. So when the moisture content in the air and the food becomes equal, okay, that is when you attain the equilibrium relative humidity. So during this, there is no, when the moisture content is equal, there is no driving force to push the water out or to get the water in, right? That's why there is neither a loss of water or gain in water or moisture. Okay, at equilibrium, all water activities equal the surrounding water vapor pressure. However, equilibrium is often slow to achieve. Equilibrium happens very slowly. Okay, to achieve equilibrium, we have to give enough time for the food. Yeah, let us see the thermodynamical facts of water activity. So thermodynamically, the water activity of a food describes the energy state of water in the food. Okay, energy is the driving force for processes to happen. We know that. So any process to happen, you need energy. So energy is the driving force. More energy means more work. Therefore, higher water activity will have higher energy that will allow the water to do more work. That means that food becomes less stable. So we want to convert this higher energy state to lower energy state to reduce the water activity and then increase the stability of food. Okay. Yeah. A proportion of the total water in a food is strongly bound to specific sites. So this is about the bound water. Some water is strongly bound to specific sites like hydroxyl groups of polysaccharides, carbonyl and amino groups of proteins, and hydrogen bondings. When all sides are occupied by adsorbed water, the moisture content is monolayer value. So monolayer value is nothing but the value of the bound water. Okay, monolayer value gives the value of bound water. The monolayer value therefore represents the moisture content at which the food is more stable. Okay, so if we know the monolayer value, then we can understand at which moisture content level the food will be more stable. At moisture contents below this level, there is a higher rate of lipid oxidation, and at higher moisture contents, Maillard browning and then enzymatic and microbial activities are promoted. So for example, in gelatin 11% of moisture, starch 11%, amorphous lactose 6%, and whole spray dried milk 3%. So in this, if you remove the moisture below this, so you will have many problems like lipid oxidation, or if you go above this moisture content, so you will be seeing the enzymatic browning or microbial activities. So it is very important to get that exact monolayer value, okay, exact content of moisture. Okay, the next topic is sorption isotherm. So as I told you before, so a portion of the total water content in the food is strongly bound to specific sites. So with some bonds like hydrogen bonding or maybe ion dipole bonds or by other strong interactions. The binding action is referred to as the sorption behavior of the food. So sorption behavior is nothing but the binding action of the food. Okay, binding of the water molecules to the food. The most successful method for studying the sorption properties of water in food products has been the preparation of sorption isotherms. So you already know what is sorption, right? So sorption is the binding property of food or the water content in the food. So isotherm, iso means same, right? Therm means temperature. So in a constant temperature, we are causing this binding action. Okay, so by doing this process, we will get to know the sorption properties of water. The food sorption isotherm describes the thermodynamic relationship between water activity and the equilibrium of the moisture content of a food product at constant temperature and pressure. Okay, so look at this graph. In this graph you can see two things. One is adsorption and desorption. We have two types of sorptions here. One is adsorption, the other is desorption. So adsorption is taking the moisture content or water content inside the food, and desorption is losing water content. Okay. Sorption isotherms can be generated from an adsorption process or a desorption process. The difference between these curves is defined as hysteresis. So you can see a gap between these two curves, right? So this region is called hysteresis. So this is common in any kind of adsorption and desorption curves. Let us see about this graph. The water in region A, so that is in this region, in the first region, it represents strongly bound water. Bound water is unfreezable and it is not available for chemical reactions. So the next region, the middle region, B. Okay, so in this region, water molecules bind less firmly than in the first zone. They usually present in small capillaries. So in this region, water molecules are not bound strongly. Okay, they can be mobilized. So this region is less stable and we can get the free water from this region. And then in the third region, that is C, this region it is similar to the B, where the free water that is held in voids and large capillaries, the water content is loosely bound to foods, so they can undergo desorption very easily. Okay, in the C region. Yeah. The next topic is influence of the water activity on the products, on the food products. Okay. Water activity is not only responsible for the growth of undesirable organisms which produce toxins or other harmful substances. It is also responsible for various other problems in the food products like microbiological stability, then chemical stability, which involves the Maillard reaction, then content of proteins and vitamins, then color, taste and nutritional value, then stability and durability of the food product, and solubility and the texture of the food product. So water activity affects all these properties of the food. Therefore, control of water activity is essential in the food industry for the products, to get good products. Let us see the relation of water activity to food spoilage. So first one is water migration. When the water activity of a material is less than the surrounding water vapor pressure, there is a driving force for the water molecules into the material. So we already studied this before. So if there is a driving force, if there is a gradient in the vapor pressure from the food to the environment, the surrounding air, so then the water will go outside the food or inside the food, okay, according to the gradient. Whereas when the material's water activity is greater than the surrounding water vapor, the material will lose water. So if material has lesser water content than surrounding, from surrounding the water content will get into the food. If the food material has more water content, so the water content from food will go out into the surrounding. The water migrates from regions of high water activity to the regions of low water activity, and it does not migrate between areas of unequal moisture content. So we studied the difference between moisture content and water activity, right? So the water moves only in the higher concentration of from the higher concentration of free water to the lower concentration of free water, right? So it doesn't consider the bound water. Water migration between different layers of multi-component food can cause undesirable textural changes. Okay, so this causes the food spoilage. Okay, even the water coming out from such food may facilitate the growth of microorganisms. Okay, so here we can see one is apples and the other one is the fried foods. So in apples, so you can see the apples are shrunk, that is because of loss of moisture. So in fried foods, if it is kept in a high moisture content room or in a storage area, then these crispy fried foods might become soft and soggy, which is not favorable for its texture. Yeah. Next is the relationship of water activity and the Maillard reaction. So we all know that Maillard reaction is a chemical reaction between amino acids and reducing sugars that gives brown color to the food. Okay, so Maillard reaction is favorable in many processes, especially in bakery industry, right? In browning of the brown layer of the buns or the cake or bread. So all that brown layer is got by Maillard reaction. It is favorable, but in some cases it is not favorable. Let us see about it. Water activity is believed to be one of the important factors in controlling the Maillard reaction. The product of the Maillard reaction leads to a darkening of color, reduced solubility of proteins, development of bitter flavors, and reduced nutritional availability of certain amino acids like lysine. So in the definition itself you can see that some amino acids will react with the reducing sugars, right? So such amino acids will be lost. So for example, we have lysine. Okay, lysine usually goes for Maillard reaction. Okay, especially in milk. As water activity approaches 0.70 in all substances, the rate of the Maillard reaction and sugar browning, so it increases. Okay, so that's why water activity is very important in controlling undesirable Maillard reactions. So water activity about 0.7 will trigger the Maillard reaction. Okay, higher than 0.70 Maillard water activity below 0.70. So if it is higher, the Maillard reaction slows down because all those components, amino acids and reducing sugars, which involves in Maillard reaction, that will be dissolved, they will be diluted, so they won't be causing any non-enzymatic browning. Okay, non-enzymatic browning causes spoilage during the storage of dry milk, dry whole eggs and breakfast cereals. Let us next see about the relationship between water activity and microbial growth. The lower the water activity value, the more dry a food item is considered. The higher the water activity, the faster that microorganisms like bacteria, yeast and mold will be able to grow. Reduction of water activity in foods prevent the growth of vegetative microbial cells, germination of spores and toxin production by molds and bacteria. A decrease in water activity increases the lag phase of microorganisms. So lag phase in the microbial growth curve is the phase where the microbial growth will be least, okay, will be very slow. Okay, this water activity, if it is decreased, then the lag phase of the microorganisms will increase. Okay, and this will decrease the growth rate of the microorganisms. most pathogenic bacteria need a water activity of 0.9, while spoilage molds need at least 0.7 or higher for growth. So here is the table which gives different water activity for different kinds of microorganisms. For most bacteria, the favorable water activity is 0.91 and above. For example, Salmonella species, Clostridium botulinum. Then for most yeasts, the favorable water activity is 0.88. So example, Torulopsis species. And for most molds, the favorable water activity is 0.8, and the microorganism example is Aspergillus flavus. And then for halophilic bacteria, so they are basically the salt loving bacteria, so they need around 0.75 of water activity, example Walamias AB. Then xerophilic molds, so which can grow in low temperatures, so they require water activity of 0.65, and example is Aspergillus aculeatus. And then osmophilic yeast, they require 0.60 of water activity, example is Saccharomyces bisporus. Okay, so any microorganisms, just like humans, they require water for all their metabolic processes. So if we cut that, if we give not enough water for them, so their growth will be the growth rate will be slowed down or it is stopped. Okay, yeah. So let us see the importance of water activity in food industry. So by measuring and controlling water activity of foods, it is possible to predict which microorganism will be potential sources of spoilage and infection. So we can predict the growth of a particular microorganism in different water activity. Then it will also help to know and to maintain the chemical stability of foods, and it will also help to minimize non-enzymatic browning reactions. The study of water activity will help us to minimize spontaneous autolytic lipid oxidation reactions which will take place in very low water activities. Okay, then water activity studies will also help us to prolong the activity of enzymes and vitamins in foods in required areas. And also it will help us to optimize the physical properties of food such as texture and shelf life. So these are the importance of water activity in food industry. So that's all about today. It was a very small topic, but yet it is very important in food industries. So goodbye for today. For any query, you can call the number on the screen. We will meet again in the next session in the same platform. Continue your preparation with IIOCS.com. Food Tech Club. Thank you.